Hi there, this is lesson 10.1 on sequences as functions. So our objectives in this section is we're going to relate arithmetic sequences to linear functions and geometric sequences to exponential functions. So we have a lot of vocabulary, so let's go through the majority of the first. So we have sequences. What is a sequence? It's just a set of numbers in a particular order or pattern. What's a term? Well, each number is called a term and it has a specific position. Like the first number is term 1, the second is term 2, the third is term 3, and so on and so on. A finite sequence is a sequence that contains a limited number of terms. For example, I could write, I use a brace, I could say -2, 0, 2, 4, 6. So this is a finite sequence because I have exactly 5 terms and only 5 terms. All right, what's an infinite number of sequence? Well, infinite means it continues without end. For instance, when we denote counting numbers, we go 1, 2, 3, comma, dot, 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 right? Those 3 little dots are called ellipses. And that just means it continues with this pattern forever to infinity. So that's what an infinite sequence is. Now we have, we're going to talk about 2 types of sequences. We're going to talk about arithmetic sequence and a geometric sequence. But let's start with arithmetic sequence. Basically, it's a sequence which each term is determined by adding a constant value to the previous term. And that constant value is called the common difference, which is your other vocabulary word. So that's what a common difference is. Now, let's look at sequence as a function. So when a sequence is a function in which the domain consists of natural numbers and the range of real numbers. So basically we're saying all the x's, the domains, independent values, are natural numbers, which is another name for natural numbers is counting numbers. 1, 2, 3, so on and so on. The range consists of real numbers. So the domain is the position of the term. The range is actually the term of the sequence. So for instance, if I have 3. So here the domain would be 1 and the range would be 3, 2, 6, 3, 9, 4, 12, 5, 15. So these are the domains arranged as the x, y values. Okay, in an infant, it would go on forever and ever. Okay, that's what the ellipse is. So that's all we're saying is a arithmetic sequence. The domain is the position or counting numbers, and the range is the actual number. All right, so let's determine whether each sequence is an arithmetic sequence. So let's look at the first example. So we take the numbers 5, comma, -6, comma, -17, comma, -28. We said is there a pattern? How do we get from here? So we added, what do we add? -11. Do we add -11 to here? Yes. And do we add it between here? Yes. So this is called a common difference because we've added 11 to each term to get the next term. So this is an arithmetic sequence. Let's look at B, -4, comma, 12 plus 28, comma, 42, sorry, comma, dot, dot, dot. All right, so from here to here, I've added 16. From here to here, I've added 16. From here to here, I've added 14. Uh-oh, do I have a constant value, a common difference? I did here, but from here to here, from these 2 terms, I don't. So this is not an arithmetic sequence. All right, do the practice problems 1A, 1B, and let's move on to example 2. All right, so example 2 says, consider the arithmetic sequence 18, comma, 14, comma, 10, comma, dot, 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 okay? And they want us to find the next 4 terms. So this is term 1, term 2, term 3. So the first thing is we have to find, I'm doing what? I subtracted 4 to get here. I subtracted 4 to here. So my common difference is -4. So then I take 10 minus 4 is 6. 6 minus 4 is 2. 2 minus 4 is -2. -2 minus 4 is -6. So this is going to be the 4th term, the 5th term, 6th term, and the 7th term. So the next 4 terms are 6, 2, -2, and -6. Now they want us to graph these. So remember, they're just x and y values or coordinates. So you have 1, 18, 2, 14, 3, 10, 4, 6, 5, 2, 6, -2, 7, -6. And then we know how to graph coordinates. I hope you do. 6, 7, 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so I'm going to do these by 2. So this is 18. I'm going to do these by 1. Okay, so 118 is going to be here. 2, 14, 16 is here. And then 3, 10. And then 4, 6. And then 5, 2. And then 6, -2. And then I get 7, -6, which is down here. And you notice the pattern, it lies on a what? On a line, which we call a linear equation. So note the pattern that the graph of arithmetic sequences are in the pattern of a linear equation. And n, meaning n is the term, the independent value, and then the term a sub n is going to be the dependent value, and that's the actual value. So this is n here, and this is a sub n. All right, the xy. So pause the video and do guided practice 2. Let's move on to example 3. It's a real-world example. It says refer to the beginning. So what they tell us at the beginning, there's a marching band. They march in rows. So the first row has 1 band member. The second row has 3. The third row has 5. And they said, so this is row 1, row 2, row 3, and it continues in this pattern. Suppose the director wants to determine how many performance will be in the 14th row. Okay, so we could actually do this pattern, making 4 to 14th rows and do it. It'd be tedious, but it's not too bad. But in other words, let's find a different way of finding this. Let's use the equation instead of drawing this out. Because what if I wanted to find they had 85 rows? I don't want to do this 85 times. This will take me a long time and I could make a mistake. So we said it's a pattern of a linear equation. So we can use the point slope formula, which is y, again, using algebra stuff, equals m times x minus x1. So we know that this coordinate is 1, 1. This is 2, 3, and 3, 5. And we know that the common ratio is we add it 2 and we add it 2. So, the common difference. So the common difference is 2. All right, so we can put any point and the common difference as the slope into this equation, and we get y minus 5 equals 2 times x minus 3. So we're using the slope for the common difference. All right, so y minus 5 equals 2x minus 6, y equals 2x minus 1. So here's our equation. So if I wanted to find, remember that D independent is the term. The 14th row is the term, the 14th term. So I want to find f of 14. I can put it in here. So 2 times 14 minus 1 gives us there's going to be 27 band members in row 14. All right, so we're just using point slope because it's in the form of a linear equation, and we're using any coordinate, any x, y, and the common difference as a slope, and then we can solve for whatever term we're looking for. All right, pause the video and let's go on to example 4. Oh, do the guided practice. Okay, so we're going to our last 2 vocabulary words, which is a geometric sequence and a common ratio. So a geometric sequence basically is just a sequence where the term is determined by multiplying, not adding, a common value to the previous term. And that common value is called the common ratio. So that's the value that's multiplied by the previous term. All right. So For example, if we have this sequence, 1 over 16, comma, 1/4, comma, 1, comma, 4, comma, 16, right? 14. So what do we multiply 1/16 by to get 1/4? We multiplied it by 4. Yes? And then we multiplied this by 4 to get the next term. And then we multiplied by 4. And, oh, this is 1, comma. So by 4 and then by 4. And that's called a common ratio. Okay? So let's look at example 4. Determine whether the sequence is geometric or not. So we have -2, 6, comma, -18, comma, 54. Now, using your algebra skills. So if I say 2 times, I'm going to call it R for ratio, equals 6, the next term, correct? Because we're multiplying the common ratio. How would I solve for R? Wouldn't I divide by 2? And I got 3. So here, if I do 6 divided by -2, I get -3. If I do -18 divided by 6, I get -3. And if I do 54 divided by -18, I get -3. So what I'm really doing is I'm multiplying each term by -3. That is my common ratio. It's the same, so it is a geometric sequence. Let's look at example 4b. We have 8, 16, 24, and 32. So we're going to take 16 divided by 8, and we get 2. Then we're going to take 24 divided by 16. Let's see, we divide by 4, we get 6. Divided by 4, we get 4. Divided by 2, we get 3. Divided by 2, we get 2. We get 3 halves here. That is not equal to 2. And then if we do 32, and I might have done bad math here, divided by 24, divide by 8, we get 4. Divide by 8, we get 3. 4/3 definitely is not equal to 2. So we don't have a common ratio, so it's not a geometric sequence. All right, now go ahead and pause and do the guided practice, and we'll move on to example 5. Now consider the sequence 32, 8, and 2, ... It's a they tell us it's a geometric sequence. They want us to find the next 3 terms. So remember, this is 1, 2, 3, and we need to find term 4, 5, and 6. So the first thing we're going to do is we're going to find the common ratio. So it's 8. It's always 8 divided by 32. It's not always the big number divided. It's the term divided by the previous term. We get 1/4. And then 2 divided by 8 is 1/4. So my common ratio is 1/4. So I'm going to take 2, I'm going to multiply it by 1/4. Got to know fractions. 1/2. 1/2 times 1/4 is 1/8. Don't forget how to do basic fractions. I think that's where you're going to struggle here with. And 1/32. So we get the fourth term. Let me do a different color. The fourth term is 1/2. The fifth term is 1/8, and the sixth term is 1/32. So those are our next 3 terms. Now they want us to graph the first 6 terms. Well, what are they? 130. So this is my x values, and these are my y values, correct? So you see the coordinates 132, 2, 8, 3, 2, 4, so on and so on. So I'm going to graph it, except for I'm going to just make this 32. I'm not going to put 32 lines. And then I'm going to make these 1, 2, 3, 4, 5, 6 really small. So 132 is the first one. Okay. The second one is 2, 8. So that's going to be way down here. Next one is 3, 2. And then 4, 1/2. 5, 1/8. And 6, 1/32. Okay, do you notice the pattern? It's a what? It lies on an exponential function. Hence, notice that in arithmetic we have a linear equation, and in exponential we have and in geometric we have an exponential function. So this is the decay. So remember, exponential has 2. So it could do this, right? It could go up that way. So notice the pattern. One's a linear, and one's an exponential. All right, pause it, do the guided practice 5, and let's move on to example 6. So now we want to determine whether each sequence is arithmetic, geometric, or neither. So let's take 16, 24, 36, and 54. So we're going to do 24 minus 16 is going to give me 8. 36 minus 24 is going to give me 12. And 54 minus 36 is going to give me 18. So I don't have an arithmetic. I'm just going to call it A. I'm not going to write it all out. So for a geometric sequence, let's check that. So we're going to do 24 divided by 16, 36 divided by 24, and 54 divided by 36. So let's reduce. I know 4 goes into this 4 times, and this, why does that not seem right? But it does. So this is 3 halves. Here we divide by 6, we get 6. Divide by 6 is 4, we get 3 halves. And same thing here, we reduce this down, we get 3 halves. Okay, so we have a common ratio. We multiplied by 3 halves, so we have a geometric sequence on 6A. Let's look at 6B. 1, 4, 9, 16. So you're just going to do 4 minus 1, 9 minus 5, and 16 minus 9 is 7. So it's not arithmetic. 4 divided by 1, 9 divided by 4, 16 divided by 4. Okay, so this is, divide by 9. Okay, so no common, this is 4, and I know 4 does not equal to this or this, so we do not have we don't have a common ratio, so therefore it's not a geometric sequence, it's neither one of these. Let's look at 6C. We have 23, 17, 11, 5. So we subtract 6, right? We subtract 6 here. We subtract 6. So we have looks like we have a common difference. So it looks like it's arithmetic, but let's just make sure it's not geometric, because there's no way it's going to be both. But I just always like to be cautious. So, well, these two are not equal right off the bat. So it is not geometric. So we have an arithmetic sequence in this one. So stop the video, do the last 3 guided practice, and we will see you in class.